we've just seen is a homemade simulation of a sunset, only using water, milk and a flashlight. And in order to understand how this works, let's maybe first talk about how natural sunsets work and why they're so gorgeously red, as we know them. Okay, so imagine we have the sun, and what we also have is the Earth and its atmosphere. So the Earth is protected by a large layer of air and other particles which are meant to protect us from solar storms and so on. But what happens when a beam of light hits the atmosphere? Well, the point is that this beam of light, that this light is scattered in the atmosphere, and the blue parts of the light are scattered more. Why that's the case I'll explain later, but the blue part of the light is scattered more than the rest of the light, which is why in the end the sky appears blue to us, while the sun still appears yellowish white. And the reason or the rule why blue light is scattered more than the rest of the light is Rayleigh scattering. And Rayleigh scattering is a rule which basically says that the amount of scattered light is proportional to 1 over the wavelength of the light to the power of 4, which is why blue light is scattered way more than, for example, red light, because blue light has a wavelength which is shorter than the one of red light. Okay, now let's talk about sunsets. So imagine you're a person on a point on Earth where the sun is just setting. The question is, what happens now to our beam of light? So the beam of light which has to go to your eye has to go through much larger distance of atmosphere than before, because you're just at the point where the sun is setting. That means there's more space, more distance where the light can be scattered, so there'll be more scattering out of blue light than before. So what's left is even less blue light than before. So in the end, what's left, what can be seen by your naked eye is, well, you could have guessed it, obviously, red light. Or some kind of reddish light, because there's also obviously other colors, but red is the one who dominates in the end, which is why sunsets are red. So now let's dive into a little bit more details about why Rayleigh scattering works the way it works. Okay, so what we've learned now is that blue light is scattered more than the rest of the light due to Rayleigh scattering. But why is blue light scattered more? Why is there a preferred frequency of light? Why can't there be an equality of frequencies? Why can't all frequencies be scattered by the same amount? And in order to understand this, we have to understand how electromagnetic radiation is made. Okay, so one thing I think many people might know from school is that if you have a charged particle, this particle will have an electric field. And if you move it, it'll also have a magnetic field. So if you keep moving a charged particle up and down, what you'll get is an electromagnetic wave. So you'll get electric and magnetic fields which penetrate space. And that, so moving a particle, a charged particle up and down in order to get a wave is called a Hertzian dipole. And that's how electromagnetic radiation is made, basically. Okay, so as a next step, in order to understand why blue light is scattered more than the rest of the light, we have to understand the concept of eigenfrequencies. So for example, if I have a pendulum here and I let it swing, oscillate, there's some kind of eigenfrequency to this pendulum, which means there's always this frequency where it'll come back to. Even if I start pushing it and pushing it and pushing it, it'll always come back to its eigenfrequency. It'll always oscillate in the same time back and forth. So there's no real way I can use, or no real method I can use in order to make this oscillate faster or slower. And that's the same with particles, at least by a certain degree. That means that, for example, this amazing proton also has an eigenfrequency. So if you stimulate this proton with the right light, for example blue light, which has the correct frequency, then this proton will start to oscillate more and more and more. It's like pushing a pendulum with the right frequency. Whereas if you have the wrong frequency, for example red light, it won't stop oscillating at all, because this frequency doesn't fit the eigenfrequency of the proton, which is why blue light is scattered more, because blue light makes the protons or the electrons in the atmosphere oscillate, which makes them emit radiation in the frequency of blue light, which is why blue light is scattered, whereas red light won't make the atoms or the electrons or protons oscillate as much, which is why there's no much red light radiation emitted by the charged particles in the atmosphere. Okay, so what we've learned now is that blue light is scattered more than the rest of the light, which is why the blue sky is blue as it is. And in the evening, the light has to go through a longer layer of atmosphere, which is why more of the blue light is scattered out, which is why more of the red light is left, and which is why the sun and the rest of the sky appears red in the evening. So now to make ends meet, let's get back to our experiment. First thing we need is plain water. Then we can start shining light through the water, but the only thing I can see on the wall is a white spot. There's already going some scattering on in the water, it's a little bit blue, but there are still many particles missing. So I need something which scatters the light even more than water, which in my case was milk. So we can now try again to shine light through the mixture of milk and water, and we can see nothing really, because all the light is scattered out. The mixture is too dense, no light is left after passing the mixture, which is quite bad. So what we can do is take the mixture and put a little bit more water and less milk into it. And looking from above, we can already see some reddish, orangish stripes in the water. But let's now turn off the lights and try it again with a real flashlight. And indeed, we've now realized our first own homemade sunset, made only with milk, water and the flashlight. And I'll now let you enjoy the rest of the video.